6C. So in 6C, we really start looking at, well, what does the standard deviation mean? And why do we care? Okay, so the normal distribution is symmetric. It's a bell-shaped distribution with a single peak. Its peak corresponds to the mean, median, and mode of the distribution. Its variation is characterized by the standard deviation of the distribution. Another name for normal distribution is the bell-shaped curve. One of the things that a lot of teachers do that I always could not stand was whenever they said, I'm going to do my grades according to the bell-shaped curve. Okay, and so what that means is that it doesn't matter. Let's just talk about this. So if this is the bell-shaped curve kind of looks like this. So these people, that means that a C would be the grade that was given most amount of times. We have the A's over here and the F's over here. So that can mean a couple of things. It could mean that I worked my tail end off, but my grade, it ends up being a C because they are bound and determined to give this many C's. And so the people at the very, you trying to fix the slide? Did you need in here?
Well, I've got
Oh, yeah. That's where I'm not the person, but yeah, that's where they want it. No problem. So on a bell-shaped curve, sorry about that disruption, they're going to give this many C's regardless of how well the person does. So let's say that the average grade in the class, like if we didn't do the bell-shaped curve, was really 90. Well, that teacher is going to adjust that so that the people that make a 90 really make a C, okay? And maybe the people that make a 99 are the only ones that end up with an A. Okay, and that can also work in a negative way. It could also encourage students to not try because they think, well, I think I'm about as good as everybody else in here, so I'm guaranteed a C. So they don't even try because there's very few people that are going to fall in this F category. So I would rather get the grade that I earn, not the grade that is according to bell-shaped curve. But that is what a normal distribution is. So when we look at some graphs, it says the normal distribution arises quite frequently and describes many data sets concerning human characteristics. This figure shows two distributions. A shows a famous data set of the chest sizes of 5,738 Scottish militiamen collected in about 1846. So if we compare those, that's a human characteristic. So it does kind of match the bell-shaped curve. It goes up, comes back down. We've got about an even distribution on the left and the right. So that would be something that's going to match that bell-shaped curve. Okay. B, it says the normal distribution of population densities of the 50 states. Well, we know that there are some states that have a lot more population per area than others. And so this has, in fact, we've got in this category, we've got about 30 in this group that have a population density that is very low. Once we get up here to 1,000, these are probably your bigger cities or bigger states like California. It has more population per area of land because that's what population density is. So this is not a bell-shaped curve at all. It's not symmetric. It doesn't go up and come back down. So this one would be an example of a normal distribution. It makes the bell-shaped curve. Sorry about that, can't spell today. And this one is not normal. Okay, in fact, on 6B, we talked about data being skewed. Okay, there's a lot more data on this side of the table. This is actually data that has been skewed since there's more data on the right. I'm sorry, that's the left. There's more data on the left. This is skewed right. Got a lot more data on this side, so this one would be skewed right. It's the opposite of what you think. So that's an example of that. It's not normal. Okay. So it says which distribution below appears to be normal? Well, this one, right? This one is not terrible, but this is way more goes up, comes back down, right? This one's kind of has more data to the right, I mean to the left, so it would be skewed right, but it's not a terrible distribution. But this one's so perfectly normal. This is the one that represents a normal distribution. So what is normal? In general, any quantity that is the result of many factors is likely to follow a normal distribution. For example, adult heights, scores on SAT tests or IQ tests, sports statistics. So conditions for normal distribution, this is important. Most data values are clustered around the mean, giving a well-defined peak. So you're looking for something that goes up, comes back down. We've got one peak and it's well-defined. So if you go back up here and look at this other example, I said it wasn't terrible, but this doesn't really have a well-defined peak. I could even say it goes up, comes back down, goes up again, comes back down, goes up again, right? It's not terrible, but there's some ebbs and flows in it that make it not one peak. Data values are spread evenly around the mean, so it has some symmetry. Symmetry means you can fold it in the middle, right? And it's the same on both sides. Tapering tails on each side. So we start in the middle's big, tapering tails means to both sides it kind of gets smaller. The individual data set results from a combination of many different factors such as genetics and environment. So usually things that are normal are going to have these qualities. Data values are resulting from combination of many different factors. So if we consider these two examples. So number one, if we talk about the scores on a very easy test. Okay, well, what happens if you got scores on a very easy test? Is that going to be normal or not? And so if I give a very easy test, most likely people are going to make 100 on it. There might be an exception to that rule, like we might have one or two people that do bad, but almost everybody's going to make a 100. If we looked at, if we drew a graph for that, is there anything I could do? Let me move that chair out of the way. Thanks for putting that in here. So if these are our test scores, and it's a very easy test, then if 100's down here and 0 is right here, we're going to have a whole lot of people score 100 and then it's going to taper off this way. That's not a normal distribution. In fact, there's a whole lot more scores on the right, so this would be skewed left. So I said it backwards again. There's a whole lot more scores on the left, so it is skewed right. Sorry about that. Okay, the second situation says the foot lengths of a random sample of adult women. Well, as long as we sample enough women, I want to say the average shoe size is around the 7.5 or an 8 for a woman. So we're going to get some shoe sizes that are more, some shoe sizes that are less, but it's going to make like a bell-shaped curve unless our sample size is really small. If we're sampling enough people, we're going to end up with some that have a bigger shoe size, some that have a smaller, but not as many as have the mean of 7.5. So this is a normal distribution. That would be an example of something that's going to make a normal distribution. When you are doing your project 2, that's the kind of things you want to ask you to analyze these things. That's the kind of things that you want to take into account. Does this have a normal distribution? When you're analyzing your data, you want to kind of look at that stuff. Okay, so let's talk about this 68, 95, 99.7 rule for a normal distribution. About 68%, and it says more precisely, 68.3%, or just over 2/3 of the data points will fall in within one standard deviation of the mean. Now, we calculated what standard deviation was in the last lesson. Now we're kind of talking about, well, what does that mean? Okay, so about 95%, or more precisely 95.4% of the data points fall within 2 standard deviations of the mean. And then finally, 99.7% of the data fall within 3 standard deviations of the mean. Okay, so let's kind of make this where I'm going to pull up the next page too, where we can understand it and talk about it. So what does this mean? It says each test that makes up the SAT is assigned so that its scores are normally distributed with a mean of 500. All right, so in this problem on this graph, that means that this score right here is 500. That's my mean. They told me that in the problem, and that's where it would be on the graph. It has a standard deviation, so this is important. My standard deviation is 100. X bar means mean, and a mean of 500. So what does that mean in this 68, 95, 99.7 rule? Draw a picture. Okay. So on this paper, you can see that when we look at the 68, it says that we would subtract 1 standard deviation to get this value. I'm going to go kind of slow on this because it's very easy, but people get confused. We could subtract 1 standard deviation to go this way, or we could add 1 standard deviation to go the other way. Okay, and they told us what standard deviation was. They said it was 1 standard deviation was 100. Okay, so in this problem, if I subtract 1 standard deviation, well, 500 minus 100, 400. If I add 1 standard deviation, I'm going to be at 500 plus 100, which is 600. In this problem, what that means is that 68%, if we're following that rule, 68% of the scores for the SAT fall between 400 and 600. They're 1 standard deviation away, both directions. If we go out to the 95%, this time we're supposed to subtract 2 standard deviations. And if we go the other way, we're supposed to add 2 standard deviations. Well, if we start with 1 standard deviation in this problem, they told us was 100. So if we do 500 plus 200, right, because we're adding 2 standard deviations, so that would be 200. We would be at 700. If we do 500 minus 2 standard deviations, well, 500 minus 200 is going to be 300. So now they're telling us that 95% of the scores are going to fall between 300 and 700. Okay, they're 2 standard deviations away in both directions. Okay, now, so we're doing the 68, 95, 99, and I think they go ahead and say 99.7, don't we? Just want to make, yeah. 90, so they rounded these two, 68, 95, and they're saying this one's 99.7. So if we stretch it out one more, well, we went 1 standard deviation, 2 standard deviations. Well, it would only make sense that this is 3 standard deviations away. So that would be adding 3 standard deviations. This one would be subtracting 3 standard deviations. Well, 1 standard deviation is 100, so 3 of them is going to be 300. So 500 plus 300 is 800. 500 minus 300 is going to give me 200. So 99.7% of the scores fall between 200 and 800 as their score. So the people that are out of that range, scoring between a 200 and 800 are like 3% of the data, or 0.3% of the data. So almost everybody falls in that range. That's what the 68, 95, 99.7% rule means. Okay, so let's look at one more example of this. It says vending machines can be adjusted to reject coins above and below certain weights. The weight of legal U.S. quarters are normally distributed with a mean of 5.7 or 67 grams. That's important. This number right here, 5.67 grams. On my little graph right here, that means that right in the middle, I'm supposed to have the mean, 5.67 grams. This number right here is also important, 0.0700. We don't really need these extra zeros. So our standard deviation is 0.07 grams. Right? If a vending machine is adjusted to reject quarters that weigh more than 5.81 grams and less than 5.53 grams, what percentage of the legal quarters will be rejected by the machine? So the first thing we want to do is we want to kind of go, okay, what's this? And I'm just going to kind of segment this out. I'm going to use a different color so I can show this better. This is going to be the last example because I want to really explain this. And on Friday, I'll post the video with the rest of this, but I want to really explain where we're coming up with this. So this little segment in here is supposed to make up 67% of the data. And it's supposed to be, if I go this way, I would be subtracting 1 standard deviation. If I go this way, I'm adding 1 standard deviation. Okay. So if we start out at 5.67 and we add 0.07, and then the other one would be 5.67 minus 0.07 because we're only doing one of these. We could do this in our brain. I don't know why I'm trying to do it in the calculator. But we've got 5.74, and this would be 5.60 if we add 0.07 and if we subtract it. So that means that this is 5.74 and this is 5.60. So if, in this problem, if they were going to reject it, if it fell outside of these limits, then they would reject 37% because they're keeping 36%, but they're rejecting the rest. Okay, so that would be 1 standard deviation is always, that's your 67%. Now, if we go out even farther, let's say we are, so I'm going to draw this line. We go out even farther. This part right here, all the way to here, well, that is going to be our 95%. The blue is in 95%. Okay, but that is 2 standard deviations away. So I would have to subtract 2 standard deviations this way, and I would have to add 2 standard deviations this way. So when we talk about this right here was our 67%, has to fall in between these two. Okay, now we're looking at 95%. Okay, and 95% of the data, we start out with our mean. This time we would add, you can multiply if you want to, but I'm just adding 2 standard deviations. Okay, that's going to end up being 5.81. If I subtract 2 standard deviations, I'm going to be at 5.53. Okay. Well, those numbers look really close to what I have up here. So I'm going to go back and look at my question. It says, if a vending machine is adjusted to reject quarters that weigh more than 5.81 and less than 5.53, what percentage of the legal quarters will be rejected? Well, the ones that weigh between 5.81 and 5.53, right? That's 95% of the quarters are going to weigh between 5.53 and 5.81. So the ones that get rejected would be 100 minus 95, which would give us our 5%. So if this is the problem, they're going to, and that this was the standard deviation they gave us, we would reject 5% of those quarters because they would not weigh in between these two. Okay, if they said reject the quarters that don't weigh in between 5.60 and 5.74, that would be 100 minus 67, which would be 33% of the data, right? 33% of the quarters wouldn't fall. Well, that'd be way too many. You'd have some mad customers then. Okay, so 5% of these quarters are going to get rejected because they don't weigh within 2 standard deviations. If we went out to 3 standard deviations, we're not going to do that on this problem, but if we go out to 3 standard deviations, that's going to be 99.7. So that would be like no quarters, like 0.03% got rejected. But it's not asking us to do that. So on Friday, I will finish this lesson and I will also go over 6B support. So you should be